Hello everyone, welcome to this channel. Here I started a video lecture series on tensor analysis. This is part 2. In the previous video, we have discussed about introduction part of tensors, and in this video we will talk about coordinate transformation for tensors. So first let us revise some basic concepts. So physical quantities like temperature, distance and mass, these quantities are example of scalars. And to represent scalar, what we need a value, or we can say we need a magnitude. Quantities like displacement, velocity, to represent these quantities we need magnitude as well as direction. So we need two things, magnitude plus direction. So these quantities are called vectors. So displacement, velocity, acceleration are examples of vectors. Next we have discussed about stress. So what is stress? Stress is force per unit area, and we have seen that stress at any point has 9 components and it contains magnitude, direction and plane of action. So stress is example of tensor and it is rank 2 tensor, and to represent rank 2 tensor what we use matrix. Since stress has 9 components, so we are using here 3 by 3 matrix. So every matrix is not a tensor, okay, but to represent rank 2 tensor what we use matrix. So matrix is just an arrangement of numbers, okay. So to represent rank 2 tensor we use matrix, and here stress is an example of rank 2 tensor. In first video all these concepts are explained in detail, so if you have not seen that video then please check it out first. Let's start this video. So here I have written definition of tensor. So how we define tensor? A tensor is a physical quantity which remains invariant under the change of coordinate system. That means we are changing the coordinate system, we are moving from one coordinate system to other coordinate system, but the physical quantity will not change, it will remains invariant. Then that physical quantity will called tensor, and tensor also obeys certain transformation laws, okay. So what is the meaning of change of coordinate system? So if you are changing coordinate system, that means the basis vector will change, okay. So if you have some vector v, and if you have basis vectors ei, then any vector v you can represent v in terms of linear combination of ei's, right? So I can write v as summation vi times ei. Ei's are basis vector and vi's are components or coordinates of v, right? So this is the presentation of v in one coordinate system. If we are moving from one coordinate system to other coordinate system, that means we are changing the basis vector. So let us suppose in new coordinate system we have basis vector ei tilde. So in that coordinate system the same vector we will represent v in terms of ei bar, okay. So vi bar, ei bar. So if you are changing basis vector, that means if ei is not equal to ei bar, okay, the old basis vector are not equal to new basis vector, that means we are changing the coordinate system, then the component will also change. Vi is component associated with old coordinate system, and vi bar are the components of v associated with new coordinate system. So if old basis vector is not equal to new basis vector, then the component will also change, okay. But the physical quantity, but the value of v will remain same. So let's understand with the help of some example. So here I have taken a coordinate system x, this is x axis, this is y and this is z. So we are considering 3-dimensional space, and here u is our vector and its position vector is o to a, okay. O is the initial point and a is the final point. So to find all the components of u, what you will do, from the final point, from the point A we will drop a line, okay, which is parallel to z axis on the xy plane. Since z axis is perpendicular to xy plane, then the line from A this will also be perpendicular to xy plane. Okay, so I drop a line from A to xy plane which is parallel to z axis. So this height, okay, let us suppose this line meets on xy plane at point P. So the height AP will give you component of u along the z axis. So what is this? This is u subscript z. So this is component of u along the z axis. So in this way you will find all the components. Okay, so this is your first component. Now to find out other two component, what we will do, from point P you have to drop a line on the x-axis and one line on the y-axis. But when you are drawing a line on the x-axis, you have to keep in mind that the line has to be parallel to y-axis. When you are drawing line on y-axis, then that line has to be parallel to x-axis, okay, the other axis. So here I drawn one line and this is the other line which is parallel to x-axis. So this much length, this length, okay, this length will give you component along y axis, okay, uy. Either this length or this is same as O to this red dot, okay, the lengths are same because these two are parallel lines, right? Now this much length, okay, this much length will give you component of u along x-axis. So in this way you will find all the component, and this, the height is uz, okay. So now you can write u as ux. Here I, j, k are the basis vector along x-axis, y-axis, z-axis respectively. So I can write u as ux times I plus uy times j plus uz times k. So this is our vector in one coordinate system. Now let us transform this coordinate system into some other coordinate system. So here what I have done, this is our y bar axis and this is x bar axis, okay. So in old coordinate system we have this y axis, the vertical one is z axis and this is x axis. Now we are transforming, we are keeping x axis and x bar axis as same, okay. So x and x bar are coincide to each other. We are moving y, we are rotating y axis and the new axis is y bar, and we are changing z from z to z bar, okay. So our new coordinate system is x bar, y bar, z bar space, okay. This is our new coordinate system. And let us take I bar, j bar and k bar as basis vector along x bar axis, y bar axis and z bar axis. As x bar and x are same, so this basis vector I bar will coincide with I, okay. Now we have the same vector, okay, we have same vector u, the position vector is OA. Now to find components of u, what we will do, from the point A we will drop a line which is parallel to z bar, okay. So this, the dotted line in orange color, so this is from A, I am dropping a line into x bar y bar plane and the line has to be parallel to z bar axis, okay. So this is parallel to z bar as you can see. Let us suppose it meets at point P dash, this point we have assumed P, okay. So now, so this A to P bar will give you component of u along z bar axis. Now to find out other component, what you will do, we will drop a line from P bar to x bar axis and on y bar axis. When you are dropping a line on x bar axis, the line has to be parallel to y bar axis. So see, this line and the y bar axis are parallel, and here when you are dropping a line from P dash to y bar axis, the line has to parallel to x bar axis. So okay, so this length, okay, this much length will give you component u y bar, and this length will give you u x bar. So as you can see, this, the previous one, this one is uy and this ux from P to this red dot, okay, and this height is uz. So you can easily see that uz and uz bar both means uz changed, the component changed, right? In the same way, previous in the old coordinate system we have the component along y-axis this much length, but now it has been changed. Ux in old coordinate system this much, but ux bar is this much. So all the components has been changed, right? When we are changing the basis vector, when we are moving from one coordinate system to other coordinate system, the components also changing. Okay, so but the vector is same. Okay, we did not move this vector, right? The vector remains same, but now we are writing u in terms of new coordinate system. So its component is ux bar and the vector is I bar, basis vector uy bar, j bar plus uz bar, k bar. So when we are changing the coordinate system, that means when we are changing the basis vector, the components are also changed. Okay, so but the vector remains invariant. So tensor is a physical quantity which remains invariant. So yes, in this, from this example you can easily see that the tensor remains invariant. Vector is also an example of tensor. So here we have taken a vector. Okay, vector is tensor of rank 1. So this remains invariant, but its component and its basis vector has been changed. Now let us consider some other example through which we will discuss that how the basis vector and component will change, in what manner they will change. Okay, so here I am taking two-dimensional plane. Okay, so here you can see this x-axis, horizontal axis, and this is y-axis. So we have xy plane, and then what I am taking, this is x bar axis and this is y bar axis. So this is not orthogonal. Okay, xy plane is orthogonal, but this is not orthogonal. Okay, and this is our new plane. Okay, that means in old system we have xy plane, this is the old coordinate system, and this is the new coordinate system. In old coordinate system, along x-axis, this the vector e1. Okay, how much length? This is our origin. So from O to this red dot, this is our E1. This is the length of E1, and E1 is vector. So from O to this red dot, this is the length, and along the x-axis, this is the direction of E1. So what is E1? E1 is basis vector along the x-axis. And along the y-axis I am taking E2 as basis vector. So in old coordinate system we have two basis vector E1 and E2. As we are in two-dimensional plane, so how many basis vectors we will have? We will have two basis vectors. Okay. In the new coordinate system we have x bar axis and y bar axis. So along x bar axis I am taking basis vector is E1 bar. So E1 bar is vector along x bar axis, and it has length from O to this black dot. This much it has length. Okay, and E2 bar is from O to this much length, and it is along the y bar axis. So in new coordinate system we have two basis vectors, E1 bar and E2 bar. Okay, now let us consider this old coordinate system. Okay, when you are in old coordinate system, consider, means just ignore the new coordinate system. If you are considering old coordinate system, that means we have x-axis, y-axis, and let us consider E1 bar vector. Okay, only the vector. That means I am considering from O to this much, this vector I am considering. Okay, and we are in xy plane. Okay, so this E1 bar is a vector, right? So I can write E1 bar in terms of E1 and E2, because in xy plane we have two basis vector. So any arbitrary vector, if you are considering any arbitrary vector, you can write that vector in terms of E1 and E2. Okay, so let's write E1 bar in terms of E1 and E2. So you will find first component of E1 bar along x-axis and along y-axis. So this much length is E1 bar. So to find its component, what you will do? You will drop a line from this point on x-axis and on y-axis. When you drop on x-axis, then the line has to be parallel to y-axis. Okay, since x and y are orthogonal to each other, so this is the line parallel to y-axis. Okay, orthogonal. So this much is from O to this black dot. This is your x component, and to find component along y, so what you will do, you will make a line on y-axis which is parallel to x-axis. Okay, so how much this length, so from black dot to this red dot, this is one E1. Okay, this is E1, so this is just double, right? So how much you need E1? So we need 2 E1 to make E1 tilde, right? To make E1 tilde, how much you need E2? So E2 we need only 1. Okay, so 1 E2. So E1 bar is 2 E1 plus 1 E2. In the same way, let us consider other vector E2 bar. Okay, E2 bar is this vector, this much. Now we want to write this vector in terms of E1 and E2. Okay, so to make E2 bar, how much we need E1 and how much we need E2. Okay, so how you will find component? So first you will draw a line on x-axis and on y-axis. When you draw a line on y-axis, this line has to parallel to other axis, that means x-axis, but both are orthogonal to each other, so it's easy to draw the lines. Okay, so how much this? So this is, as you can see, the component is on the negative side. Okay, so it will contain negative sign, and this much length is half of E1. Okay, so I can say this is minus half of E1. Okay, then how much the height, how much the E2 you need? So as you can say, this the complete length of one E2 is this much, and this is, you can say, this is 1/4 of E2. Okay, so 1/4 of E2. So what we have done here, we are writing new basis vector in terms of old basis vector. Okay, now let us make one matrix, and I am denoting this matrix as F. And what's this matrix? This matrix is 2, the component 2 and 1. So you will write component in column. Okay, so this is the coordinate components of E1 bar vector, and E2 bar has component minus half and 1/4. You will write component column wise. Okay, so this is the matrix F. F stands for matrix of forward transformation. Matrix of forward transformation. Okay, now next what we will do, we will express E1 and E2 old basis vector in terms of new basis vector. Okay, so what I am doing here, I delete xy plane, because now we are considering that we are in new coordinate system. That means we are in x bar y bar plane, and here we have two basis vector, E1 bar and E2 bar. So if you take any vector, you can write that vector in the linear combination of E1 bar, E2 bar. So this is x bar axis, this is y bar axis, E1 bar and E2 bar, these two are basis vector along x bar and y bar axis. Okay, now let us write E1 in terms of E1 bar and E2 bar. Okay, so what is E1? E1 is basis vector along x-axis. Okay, so previously we have this x-axis, the horizontal axis, along this much. Okay, this much is E1 vector. So to find component of E1 along x bar and along y bar axis, what you will do, you will drop a line from this point, the final point, from this point on x bar axis and on y bar axis. Okay, so let's make a line on x bar axis. When you make a line on x bar axis, then the line has to be parallel to y bar axis. So the dotted green line is parallel to y bar axis, and where it meets, here at this point. Okay, so from this point, this is our O origin. From O to this black dot, this much length is component of E1 along the x bar axis. So how much E1 tilde you need, E1 bar you need? So this is 1/4 of 1/4 of E1 bar. Okay, this is E1 bar vector, plus how much you need E2 bar. So on the y-axis, when you drop a line, so it will be on the negative side, because this is positive y bar, and after O, this the dotted orange line is the negative of y bar. So when you drop line, okay, and the line has to be parallel to x bar axis. Okay, so this the dotted green line is parallel to x bar axis, and where it meets on y bar axis, at this point. Okay, so this much length, so okay, here it meets, so this much length, sorry, this much length is component of E1 on the along the y bar axis. So how much it is? It is exactly equal to E2 bar. This length and this length is same, but it has negative sign, so this will be -1 times E2 bar. Okay, now let us write E2 vector in the form of E1 bar and E2 bar. Okay, so where is E2? E2 vector is, so let's make some other. Okay, so here this is x bar axis, this is y bar axis, and E2 is the vector, basis vector along the y axis. Okay, so y axis is the vertical axis. Okay, so this is our basis vector. Now to find its component along x bar and y bar axis, what you will do? Again, you will drop a line parallel to y bar on the x bar axis. Okay, so when you drop a line from this point to x bar axis, and it has to be parallel to y bar, so this the dotted green line is parallel to y bar, and where it is meeting on x bar axis, at this point. Okay, so this length, this much length is the component of E2 along x bar axis. So how much it is? This the complete length is E1 bar. So as you can see, this is exactly half. So how much you need to make E2? To make E2, we need 1/2 E1 bar. It is also a vector. Okay, plus how much you need E2? So to make a line, okay, from this point to y bar axis, and the axis has to, the line has to be parallel to x bar axis. So this the dotted green line. Okay, this is parallel to x bar axis, and where it is meeting? At this point, right? At this point, from this, so this much, okay, this much length, the complete from this to this much length. So how much it is? At from this to this is E2 bar, so it is exactly double 2 times of E2 bar, right? So now we have expression of E1, and what is expression of E2? 1/2 E1 and 2 times E2. Now, okay, so from this I can again form a matrix, and we are taking B. Okay, we are considering B, and in matrix what we will write? Component of E1 vector. Okay, so the component will be 1/4 and -1. You will write components in column wise. Okay, and this is 1/2 and 2. So this is B. Why I am writing it as B? Because it is matrix of backward transformation. It is matrix of backward transformation. It is matrix of backward transformation. So this is your B, and F denotes matrix of forward transformation. Okay, and if you multiply F with B, then you find out that F times B is nothing but identity matrix. Okay, so if F times B is identity matrix, that means F and B are inverse to each other. So what is F inverse? F inverse is B. So the matrix of forward transformation and matrix of backward transformation are inverse of each other. Okay, now let's, E1 and E2 are old basis vectors in xy plane, and xy old basis vectors. E1 and E2 are old basis vectors, right? So let us consider E1 as 1 comma 0, that means it is standard basis, okay, and E2 as 0 comma 1. So I am taking E1 and E2 as standard basis. Now what I am considering, I am taking f times E1. Okay, let's multiply f with E1. F is our matrix of forward transformation times 1 comma 0. When you multiply it with this matrix, then you will get 2 and here 1. Okay, now let us multiply f with E2. So what you will get, when you multiply with 0 comma 1, you will get minus half times 1 by 4. Okay, now let us multiply b with E1 tilde. Okay, so actual what you are getting, fe1, so this column vector, this is nothing but E1 tilde and this is E2 tilde. That means if you are taking old basis and if you are multiplying f with E1, f with E2, then you are getting new basis vectors. Okay, now I am taking matrix B and multiplying B with E1 tilde. So B is your matrix of backward transformation, and this is my 1 by 4 minus 1 and half 2. This is our matrix, and let us write E1 tilde. So what is E1 tilde? 2 1. Okay, 2 1. So how much it will give you? 1 by 4 times 2, so it is 1 by 2. 1 by 2 times 1, so plus 1 by 2. Minus 1 times 2, minus 2. 2 times 1 is plus 2. So this is nothing but 1 comma 0. And what is this? This is our standard basis E1. And when you multiply B with E2 bar, so what you will get? So what is E2 bar? This is minus 1 by 2, 1 by 4, right? So when you multiply it, so it is minus 1 by 8 plus 1 by 8. So it will be 0, and this is 1 by 2 plus 1 by 2, it will be 1. So it is 0 comma 1, that is E2 basis vector, right? That have considered E1 and E2 as two standard basis in the old coordinate system. When you multiply old basis vector with f, you are getting new basis vector, and when you are multiplying new basis vector with b, so it is giving old basis vector. That means the matrix of forward transformation means f transforms old basis vector to new, okay, and backward transformation matrix giving you old basis vector by using new basis vector. Okay, so f will take you from old to new basis vectors. Okay, f from old to new basis vectors, and b takes you new basis vector to old basis vector. Okay, so this is how f and b works, right? Now let's consider a vector v as 3 comma minus 2. Now we will write vector v in old coordinate system and new coordinate system. So let's first write v in old coordinate system. That means we have to write v in terms of e1 and e2. As we know that e1 is 1 comma 0 and e2 is 0 comma 1, then we can write v as 3 times e1 plus minus of 2 times e2. As e1 and e2 are standard basis, so the component and coordinate will be same. Okay, 3 and minus 2. Now let's write v in terms of new coordinate system. So e1 bar is 2 comma 1 and e2 bar, this is our new basis vector. Okay, this is what we have found here. This is e1 bar and this is e2 bar. Okay, now let us write v, okay, that is 3 minus 2 in terms of e1 tilde So let us say A is the component and the other component is B, which is associated with E2 tilde. This is E1 tilde and this is E2 tilde, right? So let's find A and B. So here we will have two equations, 3 equals to 2A minus B by 2, and the other equation will be minus 2 equals to A plus B by 4. When you solve, you will get A as minus 1 by 4 and B as minus 7. That means the coordinate, in new coordinate system, the first coordinate is minus 1 by 4. So minus 1 by 4, A is minus 1 by 4. This is E1 bar. So this is E1 bar plus B is minus of 7, E2 bar. So this is the representation of V in the old coordinate system, and this is representation of V in new coordinate system. As you can see, when you are changing the basis vector, the components are also changing, right? So here from 3 to minus 1 by 4 and minus 2 is transformed into minus 7 when you are changing the basis vector, or you can say when you are moving from one coordinate system to other coordinate system. Now let us consider the matrix F with new components. Okay, these, so in old coordinate system, the coordinates of V are 3 and minus 2, and in new coordinate system the components or the coordinate of V are minus 1 by 4 and minus 7. Okay, so here what I am considering, F with new coordinates of V. Okay, so what I am doing, F and new coordinates of V. So what is F? F is the matrix of forward transformation. So this one is F, and what is the new coordinate of V? Minus 1 by 4 times 7. So minus 1 by 4 times minus 7, right? So let's multiply it. So 2 times minus 1 by 4, so it will be minus 1 by 2, and minus 1 by 2 times minus 7, so 7 by 2. So it will give you 3, and this is minus 1 by 4 minus 7 by 4, so minus 8 by 4, that means minus 2. So this is 3 minus 2. So you can, and 3 and minus 2 are old component. Okay, so this is what? V's old component. So when you are multiplying F with component of V, new component of V, so it is giving you old component. Now let us take B and multiply B with old component of V. Okay, old component of V. So what is B? B is matrix of backward transformation. So B times old component of V. Old component of V is 3 and minus 2. Let's multiply it. 1 by 4 times 3. So 3 by 4 minus 1 and minus 3 and minus 4. So how much? This will give you minus 1 by 4, and this is minus 7. So what is this? This is new component of V, right? So when you are multiplying B with old component, it is giving you new component. That means F takes you from new component to old, and B will take you from old component to new. Okay, so the matrix F from new component to old, from new component to old component, right? And the matrix B will take you from old component to new component. Okay, and when you are multiplying F with basis vector, then what we have seen here in the, so F from old to new basis vector, right? So F, what F does? New basis vector to, sorry, old basis vector, here we have written from old to new. Okay, so old basis vector to new basis vectors, right? And what B does? From new basis vectors to old basis vectors, right? So you can say F, what F is doing? For component it will take you from new to old, and for basis vector from old to new. Okay, so it's F and B. So when you So here the nature of transformation is opposite for components and basis vector. So when you apply any transformation to coordinate system, then the component will change in one direction and the basis vector will change in the opposite direction. So this change of components and basis vector, as we have seen that when we change or when we transform from one coordinate system to other coordinate system, then what we write vector in terms of like vi times ei, and the other representation is summation vi bar and ei bar. Okay, so these two are representation. So the component will change in one manner and the basis vector will change in the opposite manner. That's why the effect will cancel out and the value of v will remain same. So that's why we say that the physical quantity will remains invariant. If you are moving from one coordinate system to other coordinate system, the component will change and the basis vector will change. But here we have seen that the component will change in one direction and the basis vectors will change in the other direction. That's why it will cancel the effect of change and the value will remains invariant. If you find this video helpful, then please like it, share it with friends, and if you are new to my channel, then please subscribe it. Thanks for watching.